Hi, for the lecture today we are going to take a look at the topic of hyperbolic trigonometric functions. These functions are very similar to the trig functions you have studied in high school, like sine, cosine, tangent, and the rest of them. The properties and identities are quite similar, even though the graphs are rather different. As you remember from the section on trigonometry in high school, there is a long list of formulas to work with, and this section has a similar flavor to it, and the way to get around those problems is to do a lot of exercises. Let's go ahead and get started. We are going to talk about the following functions. We have hyperbolic sine, hyperbolic cosine. Let's write the name of them. This is hyperbolic sine is written as sine h, sometimes read as sinh. Hyperbolic cosine is written as cosine h. Hyperbolic tangent is written as tan h. Reciprocals of these functions are called cosecant and secant and cotangent. Let's go ahead and discuss each of them. As a basic material here, we need to remember the functions that you have studied in the previous section, and that's the exponential function e to the x. What did the graph of e to the x look like? E to the x, well, you have a function that grows quickly, starts from near zero and builds up and goes up. This is a graph of e to the x. Here is 1. At minus infinity, you see the graph comes very close to the x-axis, because its height is 0. At plus infinity, the function goes very rapidly toward plus infinity. Similarly, you have seen exponential of minus x. You simply get that by flipping this picture over. Let me draw both of them on the same page, on the same axis. Exponential of minus x is gonna look somewhat like this. Now these two functions you remember from the previous sections are very easy to differentiate, like exponential of x. If you want to differentiate that, it's just itself. That's the easiest derivative formula. Exponential of minus x, of course, if you want to differentiate that, let me remind you of the general formula. If you have exponential of u, a function of x, and you want to differentiate, you get a copy of the function and just multiply by the derivative of the exponent. Here our exponent is minus x, its derivative is minus 1, so here the full derivative formula becomes minus exponential of minus x. Okay, this background material is what is needed to work with the formulas related to these 6 functions. All we are going to do is to combine these two in a variety of ways to get our formulas. It starts very simple and quickly builds up to rather complicated looking set of formulas. Let's go ahead and start. Very first formula we are going to take a look at, perhaps I start with y equal to cosine hyperbolic of x. Sometimes this is just read as cosh x. Cosine hyperbolic of x is simply defined as the average of the two functions we just looked at, exponential of x and exponential of minus x. If you add them and divide by 2, you're going to get something that's called cosh x. Well, let's go ahead quickly take a look at the graph of cosh x. Suppose this is my y-axis, this is my x-axis, and let's go ahead and graph exponential of x. Exponential of minus x, now averaging these two means picking up each of these two heights, for example this one and nearby from the other these two, taking these two and averaging them. Another way of explaining the same thing is to find the midpoint of these 2 points. Like here I find this point. Again, the emphasis was that it's halfway point, meaning going all the way up and going all the way down. These are going to be the same thing. Okay, now if I go ahead and graph my function, simply averaging these two, I get a function looking like this. Okay, so here we averaged, and here's a point we are supposed to go through, and from any other point as well. Like if I consider this vertical here, this point is supposed to be the average of these two heights, or just the midpoint of these 2 points of intersection, one up here, one down here, and this is the midpoint. So here we got cos x. You see that dip here, well, this function actually represents a lot of things you see in daily life. For example, if you have a hanging cable, just a regular cable that's hanging between 2 poles, it's going to stand in a manner that looks like this formula, looks like this graph. That is something you might discuss in your physics class or in your engineering class. Well, let's move ahead and take a look at the other function. Y is equal to sine hyperbolic of x, or sinh x. This is just difference of these two functions divided by 2. So I'm just supposed to take a difference of these two and divide them. The graph of sine hyperbolic of x let's see how we graph this function. I draw my x and y axis. There are several ways of graphing it. One of them is just to graph exponential of x, just as what we did before. Let me use another color. Exponential of x. Suppose this is exponential of x. Well, we want to subtract the other one. One way to subtract this is to take our function and multiply by a minus. That is minus exponential of minus x. That's going to look like this. Let's draw it with another color. Remember, let me remind you again, exponential of minus x looks like this. If you multiply it by minus, it flips over. It's going to be under the x-axis. So here I'm going to go ahead and graph it under the x-axis. This is exponential of minus x that has been multiplied by a negative, and so it's flipped over. Now we are supposed to take average of these two. Average of these means finding the midpoint between here and over there. Here's the easiest place to take the average. This is minus 1, that's plus 1, and here's the average right at 0. If you go toward the positive infinity, well, this is the significant factor here, and the other one is declining. When you want to take the average, average becomes essentially half of this. On the other hand, when you want to take the average of these two values on the graph, it is mainly dictated by this other curve, exponential of minus x. So average is going to be somewhere here. Now let's go ahead and just draw the average. So this is the graph of sine hyperbolic of x. Now we go ahead and discuss the other 4 functions. If you want to take a look at tangent hyperbolic of x, Tangent hyperbolic of x, you can do it one of two ways. By imitating the formulas out of trigonometry, or just by defining from scratch here. So tangent is, just as in the ordinary trigonometry, is a ratio of sine to cosine, except that now here sine hyperbolic over cosine hyperbolic. Well, sine hyperbolic, you remember here's a formula for the sine hyperbolic, and let me bring the other one as well. It's cosine hyperbolic. If I divide the two of them, 2's will cancel, and I'll have exponential of x minus exponential of minus x over exponential of x plus exponential of minus x. What is the graph of tangent hyperbolic going to look like? Well, here we need to take a look at the limiting properties to get the answer quickly. Let me start by drawing a picture. Let's go ahead and take a look at some important points. For example, at x equal to 0, what's going to happen? Well, at x equal to 0, we saw sine hyperbolic, that was 0. Cosine hyperbolic is 1. Ratio of 0 to 1 is going to be 0. Let's look at it another way. Suppose I replace x by 0 all over here. Well, exponential of 0 is 1. So here in the numerator I get 1 minus 1. In the denominator I get 1 plus 1. 1 minus 1 is going to be 0. So tangent hyperbolic of 0 is going to be 0. So that's one important point. Tangent, just like sine that passed through the origin, this one also passes through the origin. Now let's go all the way to the right. As I go all the way to the right, exponential of minus x is going to be negligible. Exponential of minus x, and x is a large number, that's a very tiny number, and you can just ignore that. So what is going to be left? Exponential of x here, and exponential of x here. When you take the ratio of you're just going to get 1. So at far to the right, we are going to approach 1. That means we have a horizontal asymptote. So let's specify that by drawing, suppose this is a line y equal to 1. As x goes toward infinity, I come close to this. So I start at 0 and I just build up and go toward that. What about at minus infinity? At minus infinity, exponential of x is a negligible quantity. You can ignore that because this graph of exponential of x becomes small at minus infinity. When you ignore this portion, what's going to be left? Well, minus exponential of minus x in the numerator, and here plus exponential of minus x in the denominator. These portions cancel out, and all you're going to be left with is just minus 1. So I'm going to approach minus 1 when I go to minus infinity. So the graph is going to start from, let's draw it in green, starts at minus 1, builds up, comes through the origin, and just goes over, and then bends over, and approaches 1 at plus infinity. So here are the graph of 3 basic hyperbolic trig functions: sine, cosine, and tangent. The other 3 hyperbolic functions are not used as much. You don't see them on the calculator, for example, but we need to quickly go over them as well. We can just simply refer to them in the following way. For example, suppose I want to take a look at y is equal to secant hyperbolic of x. Well, how is secant defined? You have one of 2 ways. One is just to go through the definition from trigonometry. Secant is 1 over cosine. I can define it as 1 over cosine hyperbolic of x. Another way is just to use the formula, that is, since we define cosine hyperbolic by this, then the reciprocal of it is going to have the 2 in the numerator and these items in the denominator. So that's what I'm going to write here. It's going to be 2 over exponential of x plus exponential of minus x. So that's secant hyperbolic. How does the graph of this one look like? Well, you can graph it one of two ways, using the idea that this is reciprocal of cosine hyperbolic. Another way is just to look at this formula and graph it from scratch. So let's go ahead and do the graphing the best we can. Well, let's go ahead and take a look at some important points. For example, at x equal to 0, this is 1, this is 1, so denominator is 2, 2 over 2 makes 1, so we are going to be at 1. Let's assume that this is 1. Now if I go far toward right on x equal to infinity, this is a very large quantity, and that is negligible. At any rate, 2 divided by this large quantity is going to be a small quantity. So at far to the right, I approach the x-axis. That's going to be my horizontal asymptote. On the left also, when x goes to minus infinity, exponential of minus x is going to be a large quantity, while this one is negligible. Still, 2 divided by this large quantity is going to be close to 0. So here is an important point on the left. So we have 3 points, and we can also fill up this graph with other points, but we can already guess how it's going to behave. As you go toward infinity, this is going to decline in either direction, so the graph is going to look kind of like this. So this is a graph of secant hyperbolic of x. Another way of getting to this graph is to remember what the graph of cosine hyperbolic look like. Here's a cosine hyperbolic. It keeps going quickly toward infinity at these two ends. So when you take the reciprocal of this, since this is a huge quantity, reciprocal of it is going to be a small quantity. Similarly, at this end, reciprocal of this large number is going to be a small number down here. So the way this quickly goes up, secant hyperbolic is going to quickly decline, and that's why you see this curve kind of looking like a bell-shaped. It's not the same as a bell-shaped curve, but has some similar features. Now we need to go ahead and take a look at some let's go ahead and take a look at cosecant hyperbolic. Excuse me. Okay. Here, let's get started. Y is equal to cosecant hyperbolic of x. What is cosecant? That by traditional definition is a reciprocal of sine. That's a reciprocal of sine hyperbolic of x, or sinh x. And the formula then is going to be 2 divided by, remember how sine was defined. Sine was defined as difference divided by 2. Now reciprocal of this is going to have 2 in the numerator and these 2 items in the denominator. So that's why this formula looks the way it does. Now this function is going to present us with a new challenge. You remember sine hyperbolic at x equal to 0 was 0. When x is 0, this is 1, this is 1, they cancel each other out. When this was on the numerator, that wasn't a big problem, but in the denominator means we are dividing by 0. Division by 0 is going to create a vertical asymptote for us, so this graph is going to be a bit more complicated. So here's my x and y axis. Now here's let me give you another pointer on how to remember the graph of this. This was the graph of sine hyperbolic of x. We're taking reciprocal of this. reciprocal of a large number up here is going to be a small number. Reciprocal of 0 here is going to be a large number. So reciprocal of this is going to start at infinity and start to decline. And there's going to be a similar portion here. So that's what I'm going to go ahead and draw here. Graph of sine hyperbolic. At 0 it's going to go close to its vertical asymptote. At plus infinity it descends quickly toward the x-axis. On the negative side, sine hyperbolic is going to be negative and its reciprocal is also negative, and we are going to have a picture like this. So that's going to be a picture of a cosecant hyperbolic of x. Next item that we need to take a quick look at is y is equal to cotangent hyperbolic of x. One way to define it is 1 over tangent. Another way to define it is to divide cosine by sine. Cosine, you remember, was e to the x plus e to the minus x, and sine was e to the x minus e to the minus x. Now this graph is going to present us with all the challenges we have seen so far. We have both horizontal asymptotes and vertical asymptotes, and let's graph it perhaps here. Let's see, where does the horizontal asymptotes come from? You remember what happened to tangent? Well, when you take a reciprocal of that, reciprocal also going to have horizontal asymptotes. Let's go through the discussion again. When x goes to far to the right, when x goes to plus infinity, these two quantities here, exponential of minus x, are going to be negligible, and these two will be the same and the ratio will be 1. So that gives me a horizontal asymptote. Let's now when x is a large quantity, notice numerator is going to be larger than denominator, so we are going to be above this horizontal asymptote. When I go toward the origin, x comes close to 0. At 0, numerator becomes 2, denominator becomes 0, and 2 divided by 0 is going to be infinity. So this graph is going to be going up in that style. Similar events going to happen at negative infinity. At negative infinity, exponential of x is negligible, ratio of the remaining items is -1, and we are going to have a horizontal asymptote. Here's my asymptote at y equal to -1. This one was at y equals 1. And I'll be below this horizontal asymptote, and the graph is going to act more or less like this. Okay, that was the review of these 6 trig functions, hyperbolic trig functions, and their graphs, definitions, and the relationship to exponential of x and exponential of minus x. Now we have several challenges ahead of us. One is, what do we do if we want to differentiate these functions? Second is, what are the inverse of these functions? And the third, what are the graphs of the inverse functions? And the fourth, what's the derivative of the inverse function? So as you see that our pile of formulas is increasing quite rapidly, let's go ahead and get started. You have to look at this really as a explanation of some of the items you have already seen. For example, differentiation formulas. Let's go ahead and see. If I want to differentiate cosine hyperbolic of x with respect to x, what am I going to get? Well, this is easy. The formula was exponential of x plus exponential of minus x divided by 2. We want to differentiate that. The derivative of exponential of x, as I mentioned at the beginning, just itself. Derivative of the other one, in minus comes in front, which is just the derivative of exponent, and this constant just stays there. Be sure you don't use quotient rule. You could, but that would be a huge waste of time. This is just a constant, and as a multiplier it just stays there. Well, we look at the right hand side, see what we get. What we got here is just sine hyperbolic of x. So that is nice to see that derivative of cosine hyperbolic is sine hyperbolic of x. From trigonometry, you remember derivative of cosine was negative sine, minus sine of x. This is a common theme in comparison of these two topics, hyperbolic and regular trig functions. Every now and then they're off from each other by a negative sign. Let's go ahead and differentiate sine hyperbolic. Well, that is exponential of minus x minus exponential of plus x minus exponential of minus x divided by 2. I want to differentiate that. Derivative of the first one is just itself. Derivative of exponential of minus x, just like here, is minus exponential of minus x, and that minus times this minus that is in front is going to give plus exponential of minus x, then divided by 2. So what is it that I got? This is just the definition of cosine. So here I got cosine hyperbolic of x. So here's one nice thing about hyperbolic function is that derivative of one is the other, and so we don't have that business of negative showing up here for the regular trig functions. Let's go ahead, differentiate tangent hyperbolic. I can do this one of two ways. I can write the ratio of these two formulas and then take it from there, but here's a better one. I just write tangent as a ratio of sine to cosine. So I write this as sine hyperbolic of x to cosine hyperbolic of x. That's what tangent is. And I want to take a derivative of this ratio to remember your quotient rule. How does the quotient rule go? I have to differentiate the numerator, so I write sine hyperbolic of x. Let me make it smaller so it fits. Sine hyperbolic, I have to differentiate that. Derivative of numerator times denominator minus numerator as it is times derivative of denominator. As you see, writing the name of these functions is taking a bit too much time, so we might even go ahead and make it even shorter. It would not be standard practice. Your text doesn't write it, no books write it, but after you write these things many times in one problem, you kind of tend to think that instead of writing cosh x, I might just write c. But here for now, let me just write the full name. Now let's go ahead and simplify. Derivative of sine hyperbolic, we just saw derivative of sine was cosine. So here I write cosine hyperbolic of x. So let me drop a lot of letters there and just write cx. Here's another cosine hyperbolic of x. That is another cx. So c now standing for this whole word cosine hyperbolic minus here is sine hyperbolic of x. That's sine hyperbolic of x. Derivative of cosine, we just saw derivative of cosine was sine, so I have sine times another sine. Denominator, I have cosine hyperbolic squared. The way we write it, we put the number for the power on top of the name. So I write c2 of x. That means take c of x and square. Okay. Now we have several steps ahead of us. One is how do we simplify the numerator, and the second one is how do we simplify this fraction. Let's go ahead and do the fraction first. I'll go ahead and write the numerator. Cosine hyperbolic times another cosine hyperbolic is cosine squared. Sine times sine, that is going to be sine squared. Denominator is just cosine squared. Okay, the first thing I am going to do is to break up this fraction. This is cosine squared over cosine squared. Let me write it here. I have cosine square of x, cosine hyperbolic square of x. Here, sine hyperbolic square of x over cosine hyperbolic square of x. What happened here, let me just quickly tell you, no big mystery. If you had like 7 plus 2 divided by 5, you could break up this fraction and write it as two fractions, 7 over 5 plus 2 over 5. Just the opposite of taking a common denominator, just breaking the fraction into two parts. Now, whatever this is, it's just a copy of whatever is in the denominator, and the ratio of them is just 1. This is sine over cosine squared. I might write it as sine of x over cosine of x, each of them being squared, so I might write it like this. So what is sine over cosine? Sine over cosine is tangent. Here I have enough room to write the full name. 1 minus tangent hyperbolic square of x. So let me go ahead and capture this formula. What we got is this. If you have tangent hyperbolic of x and you differentiate that, one way to represent the result is 1 minus tangent hyperbolic square of x. Let's go ahead and box this thing so we remember. Here's our achievement. How does this formula differ from traditional circular trigonometry? Over there, if you had just regular tangent of x, you differentiate it. The answer is 1 plus tangent square of x. Here's a hyperbolic version. We have this minus sign here as opposed to plus sign. That's something to remember. Okay, I promised you that there is another way of writing the answer. You remember that in the circular trig version of this is same as secant hyperbolic square of x. That means that this numerator here had to be simplified to 1 for that to happen. Well, that becomes one interesting identity of these functions. Let's go ahead, take a quick detour of some identities for these functions, which is going to be helpful in simplifying this expression. So I'm going to go ahead and make some room here. So we are going to pause for a moment, do something a little bit different, and come back. Before we start there, let me just remind you we have 3 formulas. Derivative of cosine is just sine. Derivative of sine is cosine. Derivative of tangent is 1 minus tangent squared. Now we want to write this thing as secant squared, but we need to show where does that come from. So here, before we go to all the other differentiation formulas. Let's practice this. Some identities for hyperbolic functions. Well, what's the most famous trig formula you remember? Probably you remember that cosine square of an angle plus sine square of an angle is equal to 1. That's really the Pythagorean identity. How about the similar identity here? Well, it just turns out that if you take cosine hyperbolic of x and square that, remember we said we put the 2 on top of the name of the function, and now subtract sine hyperbolic square of x, you are going to get 1. How does this happen? Well, in fact, verifying identities in the hyperbolic case rather easier than the circular case. All you need to do is just plug in the formulas and let the algebra work its magic, and the numbers are going to come out. You don't really need to be a chess player to get these identities done. All you need is patience and perseverance to sit down and do it. So what I need to do is to replace the definition for sine and cosine, and this is going to happen all by itself. So what we are asking now is to show that this is true, prove that this is true. How do I prove it? Let's just remind ourselves what was the start of the whole story. Start of the whole story was all the way, you see how many things we have already done here. Sine and cosine, that was the grandfather of the whole thing. Here's the definition of the two functions. I'm going to take them, just plug in the formula, let the algebra work, and I'll be all done. So I come back here, cosine hyperbolic, what was that? It's exponential of x plus exponential of minus x divided by 2. That's cosine hyperbolic. I'm asked to square this thing, and then sine was exponential of x minus exponential of minus x divided by 2, square that. We want to show, so it's still a question for us, is this really true? Hopefully yes, that this is going to turn out to be 1. What do we need here? A basic identity from algebra. How do you square sum of two things? Here let me remind you, if you had a plus b and you wanted to square them, you will square first, square last, and the thing not to forget is twice the first and the second has to be inserted there. So here I go ahead and square the first one. Another thing from basic algebra to remember, if you have exponential of say b and then you raise this to some exponent n, the two exponents multiply each other. Let's see if you are over with that preparation. So exponential of x, when it gets squared, it becomes just exponential of 2x. Exponential of minus x, when it gets squared, becomes exponential of minus 2x. Now I need the twice the product term. That's going to be twice the first one times the second one, and then this is added. Well, it looks like we need one more review. What is this? Exponential of x times exponential of minus x. Let me remind you, if you had b to power of m times b to power of n, you can add the exponents. I'm supposed to write this in a different color. Okay, that is a rule of exponent. Another thing to remember is that b to power of 0, that was 1. So let me, all the review material, I put it on the side here. So if you have exponential of x times exponential of minus x, one thing you could do is to add up the exponents. When you add up exponents, you get 0. You add the exponents. Exponential of 0 by that is just 1. So this whole thing just simplifies to 2. Now we had a fraction, we still have a fraction. Remember, we were squaring the whole thing, so when 2 gets squared it becomes a 4. Let's continue. Same thing here, exponential of 2x. Now I'm subtracting this other fraction. If you have a difference here, if you have a difference of 2 items and you're squaring, if this is a subtraction, and then this is going to be subtraction, but that's still addition there. So here we are going to have exponential of 2x minus the product of these two, just like here, that's going to be another 2. And the last item squared, remember that's positive, plus exponential of minus 2x divided by 4. The question is this thing really 1? Let's go ahead and see. Well, what happens? This exponential of 2x cancels this exponential of 2x after you subtract. This exponential of minus 2x cancels this one after you subtract. You are left with 2 minus 2, which is just a 4. Common denominator is also a 4. Well, 4 over 4 is in fact equal to 1. So we showed that the left hand side is equal to the right hand side. We proved the identity. You see that it all worked through algebra. We didn't use geometry here, and unlike what you do for the proof of this, you really need the Pythagorean theorem, but now totally different approach. So we showed this very important identity here. Let me box it. Okay, how do we use these identities? Let's go back here and remind ourselves. How did we fall into that? We had cosine squared minus sine squared. Now we just showed that that is just 1. So let's go ahead and repeat this thing in abbreviated form. So taking a look at derivative of tangent hyperbolic, let's see. If I have tangent hyperbolic of x, I want to differentiate it. Remember, we said this is sine of x over cosine of x, and I want to differentiate that. Derivative of numerator sine of x, I have to differentiate that, times cosine of x minus numerator as it was times the derivative of denominator divided by denominator squared. Now sine, derivative of sine became cosine. Cosine times cosine is cosine square of x. Derivative of cosine is sine times another sine is sine square of x divided by denominator is just cosine square of x. We just showed that cosine squared minus sine squared in hyperbolic life, that's just 1. So this is 1 over cosine hyperbolic square of x. Okay, what was 1 over cosine? 1 over cosine by definition was secant hyperbolic. So 1 over cosine was same as secant. I'm writing full name, secant hyperbolic. Here we are squaring, it's squaring here also. So here's the birth of our new formula, tangent hyperbolic of x. Differentiated, you could write it as secant hyperbolic of, secant hyperbolic square of x. So that is same as a 1 minus tangent hyperbolic square of x. So that is one more item in our bag of formulas. Okay, let's go ahead and do the differentiation formulas for the other trig functions as well. The next one we have online is going to be cosecant hyperbolic of x. What is cosecant? You remember cosecant hyperbolic of x was 1 over sine. So I start from there. Sine hyperbolic of x. I want to differentiate that. How do I differentiate this fraction? You remember the quotient rule, derivative of numerator times denominator. Well, that's going to be 0 because derivative of numerator is 0, minus derivative of denominator. Derivative of denominator, we learned that it is cosine hyperbolic of x times numerator, which is 1, divided by square of denominator. Okay, now we can leave this as it is, or we can manipulate it a little bit. I can write it as minus this cosine hyperbolic of x over sine hyperbolic of x times 1 over sine hyperbolic of x. So one way to write this answer, let me make it clear, this was e cosine. Cosine over sine, that is cotangent, so that's minus cotangent hyperbolic of x. 1 over sine, that's just our original cosecant, so cosecant hyperbolic of x. So that is one formula we have for this. You had also the option of converting this to cosine times cosecant square if you wish to. Traditionally, this is the final form of this, cosecant hyperbolic of x. The derivative of it, if you want to just memorize one formula, this would be it. Next item on the line is going to be secant hyperbolic of x. Let's start with that. Secant hyperbolic of x. If I want to differentiate that, what would I do? We are doing these things essentially as a practice of differentiation formulas, while we are practicing also these main functions sine and cosine. Secant hyperbolic was 1 over cosine. I have to differentiate this. I apply the quotient rule again, just like the previous problem. Derivative of numerator times denominator, that is 0, minus derivative of denominator, that's minus derivative of denominator is sine hyperbolic of x, divided by square of denominator. I could leave this formula like this, or I can manipulate it in one of many ways, traditional ways, just to break it up the way we did here. Minus sine hyperbolic of x over, I separate cosines into two separate cosines, one here and another one here. Make some room here. Okay, I go ahead and sine over cosine, that is just minus tangent hyperbolic of x. 1 over cosine is just secant hyperbolic of x, and here's our formula. Derivative of secant hyperbolic of x is that. one formula left. How about cotangent? We have two ways of going about this. Either write cotangent as cosine over sine. The other one is to write cotangent as 1 over tangent. Either of them will do. Here, let me write it cotangent as cosine hyperbolic of x over sine hyperbolic of x. We have to differentiate that. This writing becomes a little bit long here, so I'm going to abbreviate it as cx over sx to differentiate that. How do we do this? I have to differentiate numerator times denominator minus the numerator times derivative of the denominator divided by denominator squared. Now derivative of cosine of x is sine of x. Sine times sine, I will have sine square of x. Derivative of sine is cosine, so this becomes cosine square of x. Denominator is just sine square of x. Two ways of writing this. One is to say that sine over sine is just 1, and cosine over sine, that is the cotangent. The other option that you have is to say sine squared minus cosine squared. If you remember right now, cosine squared minus sine squared was 1. That was our main identity. So sine squared minus cosine squared is going to be minus 1. So minus 1 over sine square of x. 1 over sine, and that is just a cosecant. So this becomes minus cosecant hyperbolic of x squared. So here we got here 1, 2, 3 different way of writing the answers. Just pick one that you like to memorize it with. The main thing is to be able to go from one form to the other one. Cotangent hyperbolic of x. If you differentiate that, here's minus cosecant hyperbolic square of x. So that's our formula number 6 for differentiation. What's the reason for so many formulas? We're really dealing with just one function representing itself 6 different ways. So there are many interconnections and there are many ways of writing the answers and plenty of formulas. We have now covered half of them for the functions themselves. Second part of this lecture is going to contain inverse of these functions. We are probably going to go through them a little bit faster than this. Okay, you go ahead and practice these functions, their graphs and their derivative formulas and some of the identities. Also read the text and make sure you do enough exercises so that some of the ideas sink in. Okay, good luck.